Imagine standing on a tall building, tossing an apple into the air. You know what happens. It comes back down, pulled by gravity. It's simple, predictable, and part of your daily life. But what if I told you that on the grandest scales of the cosmos, gravity isn't the only player? There's something else out there, a mysterious force pushing in the opposite direction. This force is called dark energy, and it's not just a whisper in the background. It's strong enough to shape the destiny of the universe. Right now, a cosmic tug-of-war is underway, gravity pulling matter together and dark energy driving everything apart. To understand this battle, we need to step back, way back. Picture the early universe, just after the Big Bang. Everything was hot, dense, and unimaginably chaotic. Gravity was the glue trying to hold it all together, while expansion was already at play. For billions of years, astronomers assumed gravity would eventually win. The universe, they thought, might expand for a while but then slow down. Maybe it would collapse back in a fiery big crunch, ending where it began. That seemed logical. But in the late 1990s, everything changed. Observations of distant exploding stars, supernovae, revealed a shocking truth. Instead of slowing down, the universe was expanding faster. Something invisible, something powerful, was accelerating it. This discovery flipped cosmology on its head. Suddenly, gravity wasn't the lone ruler of cosmic destiny. A new contender, dark energy, had entered the stage, and it was stronger than anyone expected. So, what exactly is gravity? To most of us, it's apples falling and planets orbiting. But in Einstein's theory of general relativity, gravity is far more profound. It's the warping of space and time by mass and energy. When the sun bends space, Earth doesn't feel a pull. It simply follows the curve of space-time. That elegant idea explains black holes, orbiting planets, even the bending of light. Gravity, in essence, is the sculptor of the universe's shape. But even gravity has its limits. On the largest scales, it tries to keep galaxies, clusters, and filaments together. Yet against the backdrop of billions of light years, something is countering its grip. Dark energy, unlike gravity, is not about pulling, it's about pushing. Think of it as an anti-gravity, a pressure embedded in space itself. Instead of gathering matter, it stretches it apart. What makes dark energy so strange is that it doesn't dilute as the universe expands. Regular matter spreads out, getting thinner and thinner. But dark energy seems to remain constant, woven into the very fabric of space. That means the more space you have, the more dark energy exists. Expansion creates more of it, and more of it accelerates expansion. A runaway effect that leaves scientists scratching their heads. So how do we know dark energy is real? The evidence is everywhere. From supernovae to the cosmic microwave background to the large-scale structure of galaxies, each points to a universe dominated by this invisible pressure. In fact, the numbers are staggering. Roughly 70% of the entire energy budget of the universe is dark energy. Matter, everything we see, touch, or are made of, accounts for less than 5%. Gravity rules our local lives, but dark energy dominates the cosmos. This raises the biggest question. Is dark energy truly something new, or is our understanding of gravity incomplete? Some physicists argue we may need a radical overhaul of Einstein's equations. Others believe dark energy is a real, exotic form of energy. One leading idea is the cosmological constant, first introduced by Einstein himself. He added it as a fudge factor, trying to keep the universe static. Later, he called it his biggest blunder. But now, it might actually explain dark energy. If true, the cosmological constant represents vacuum energy, the energy of empty space. Even when you remove all matter, space isn't truly empty.
Quantum physics predicts a sea of fluctuating energy bubbling beneath reality. But here's the catch. When physicists try to calculate this vacuum energy, the numbers are absurdly huge, off by a factor of 10 to the 120 compared to what we observe. That's the most embarrassing mismatch in physics. Another idea is quintessence, a dynamic field that changes over time. Unlike the constant vacuum energy, quintessence evolves, possibly waxing and waning across cosmic history. If real, it could explain why acceleration only began recently. But dark energy isn't the only mystery in this war. Gravity itself might not be what we think. Perhaps general relativity breaks down on cosmic scales, and what we call dark energy is just the sign of new physics.
Modified gravity theories, like F of R gravity or massive gravity, try to tweak Einstein's equations. They aim to explain a universe's acceleration without invoking a new energy. Yet so far, no alternative has matched the data as well as dark energy. While theories battle it out, the observational evidence keeps piling up. Astronomers map the universe's expansion using galaxies as markers. They measure subtle distortions in the cosmic web, and all the signs point to the same conclusion: acceleration is real. But what does this mean for the future of the cosmos? If dark energy remains constant, the universe will keep expanding faster and faster. Galaxies beyond our local group will drift away, disappearing from view forever. Imagine looking up at the night sky in 1 trillion years. The Milky Way and Andromeda may have merged into a giant galaxy. But beyond that, darkness. Other galaxies will be too far, their light forever unreachable. That's the fate known as the heat death, an endlessly expanding universe where stars burn out, black holes evaporate, and all energy spreads thin, an eternity of silence. But that's not the only possibility. If dark energy grows stronger with time, we face the Big Rip. Eventually, even galaxies, stars, planets, and atoms themselves could be torn apart by accelerating expansion. On the other hand, if dark energy somehow fades or reverses, gravity could win. The universe might halt expansion and collapse into a big crunch, rebirthing itself in a fiery reset. Which of these fates awaits us depends on who wins the cosmic tug of war, gravity or dark energy. And right now, dark energy is winning. Yet this doesn't mean gravity is powerless. In our local universe, our galaxy, our solar system, gravity still dominates. It binds stars together, keeps planets in orbit, and makes life possible. Even against dark energy's push, our Milky Way will not be torn apart. Local structures are bound too tightly. Dark energy only rules on the largest scales, across intergalactic voids. This duality is fascinating. Gravity is the sculptor of the small, dark energy, the ruler of the vast. Together, they weave the fabric of cosmic history. It's almost poetic, two forces locked in eternal opposition. One gathers, the other disperses. One embraces, the other releases. The dance of attraction and repulsion shapes everything. But for scientists, poetry isn't enough. They want answers. That's why massive projects like the James Webb Space Telescope, Euclid mission, and the Vera Rubin Observatory are scanning the skies. These instruments aim to map billions of galaxies, track cosmic acceleration, and decode the fingerprints of dark energy. The data they collect may rewrite physics as we know it. For the public, dark energy often feels abstract. But think of it this way. The ground beneath you, the air around you, the light from the sun,
all exist within a universe that's actively being stretched by this invisible hand. Every second, galaxies move farther apart. Every moment, space itself grows. And all of it is happening while you sip coffee, check your phone, or walk down the street. That connection between the ordinary and the cosmic is what makes this story powerful. You are not separate from the universe. You are part of this ongoing tug-of-war. When you feel the weight of gravity pulling you down, remember above your head, across billions of light years, an opposite force is working relentlessly, a silent battle shaping the ultimate fate of existence. It's easy to think science has all the answers, but dark energy reminds us we are still explorers in a vast unknown. The universe holds secrets far beyond our imagination. The idea that 70% of reality is invisible, unmeasurable, and poorly understood is humbling. It tells us how fragile our knowledge really is.
Some scientists even wonder if dark energy is a temporary illusion. Could it be that in a century, new data will show something else? History of science is full of revolutions. This could be the next. But whether dark energy is real, modified gravity, or something stranger, it has already transformed our worldview. The universe is not a steady march, but a race between competing forces. Think of a cosmic seesaw. On one side, gravity tries to pull everything inward. On the other, dark energy pushes outward. Right now, the outward push is heavier. This balance could shift in ways we don't expect. A new discovery could reveal hidden layers of physics, new particles, or exotic dimensions influencing the game. That's why studying dark energy isn't just an academic exercise. It's about understanding the fate of everything. Our galaxy, our stars, even the timeline of reality depends on it. As ordinary people, we might never measure galaxies or write equations, but we can share in the wonder. We can marvel at the sheer scale of forces beyond imagination. The story of gravity versus dark energy is more than science. It's a reminder of how small and yet how special we are. We live at a time when this mystery is still unsolved. Future generations may look back at us as the ones who asked the right questions, even if we didn't yet have all the answers. And maybe that's the essence of being human, to wonder, to seek, and to wrestle with forces far larger than ourselves. So the next time you drop an apple, feel the pull of gravity and imagine, far beyond, an invisible hand pulling the universe the other way. In that tension lies the greatest story of all, the battle for the fate of the cosmos.